Concrete. It's the most used building material on Earth. It was the building block of the Roman Empire. Today, it's the material for a new generation of gravity-defying skyscrapers. The raw ingredients that create this magic formula can be found in nearly every country on Earth. Yet how these simple components are mixed together can make the difference between tragedy and triumph. From the mundane to the massive. From the ordinary to the extraordinary. Concrete helped pave the way for innovation and laid the foundation for the world's greatest civilizations. Now, go inside the science of concrete. It starts out like liquid. When it dries, it becomes stone hard. This amazing metamorphosis has earned concrete the nickname liquid rock. It has served as a cornerstone of engineering for centuries. And it's a highly prized tool of construction for a reason.
It's easy to take concrete for granted. People see it in sidewalks and roads all the time, every day. But in fact, it is the closest thing to a miraculous material in construction that we've ever had.
Concrete is everywhere. It has an almost unlimited engineering potential. It can take on nearly any shape and forms the backbone of a variety of the world's construction. Superhighways, massive bridges, man-made waterways, mega dams, the world's tallest skyscrapers. This miracle material begs the question, how does it do it all?
I worked on a lot of jobs, and basically they all have a different formula for their concrete. Now, I can't imagine, the world without concrete.
The basic formula for concrete is simple. Sand, crushed rock, called aggregate, water, and the heart of the concrete mix, cement.
Cement, it is the gray, powdery material that acts as a glue that sticks all of the concrete together. It covers and coats all of the gravel, the sand, and the rock as a way of gluing and binding the whole material together.
To make cement, you need limestone, clay, and other elements like iron. These ingredients are crushed and combined into a powder that's poured into a kiln. The massive cylindrical spinning kilns heat the mixture to a temperature as high as 2,700 degrees Fahrenheit. The mixture becomes partially molten, forming a new marble-sized component called clinker. Once cooled, machines grind clinker into a superfine powder we know as cement. Cement binds the ingredients together. When added to sand, water, and crushed rock, the cement reacts, linking the raw elements into one powerful whole. Water is the key. When cement reacts to the water, it undergoes a transformation called hydration. During this reaction, a node forms on the surface of each cement particle. The node grows and expands, linking up with other nodes. It sticks to the crushed rock and sand in the mix. Cement binds these ingredients. As it solidifies, concrete becomes a building block of modern construction.
The water actually allows a chemical reaction in the cement to allow it to harden. People often think that concrete hardens by drying. It actually hardens by hydrating or getting more wet. The water in the cement mixes with a lot of the minerals and chemicals that are in the cement, and by that mixture forms a new compound which then hardens.
This basic process hasn't changed in over a century. But creating concrete is no simple matter. Making the right recipe requires precision and flawless preparation. It is a synergy of ingredients and timing.
In a way, making concrete is like making a cake. There are lots of different recipes to make a cake. You get different flavors, different colors, different textures, but there are also lots of ways that you can make a cake wrong. It's not going to set properly, or it can come out in a way that's very different from your intentions.
Getting the recipe right is everything, and the consequences of a flawed mix can be deadly. The residents of Mexico City learned this the hard way. On September 19th, 1985, the Mexican capital is rocked by an 8.1 magnitude earthquake. It causes up to $5 billion in damages. Investigation of the rubble reveals that many of the buildings had been made of a substandard concrete.
Yes, we saw examples after the Mexican earthquake where when you use inferior concrete and you skimp on the rebar, and we saw both extensively in Mexico City, the concrete doesn't have its expected strength. The result is walls would fracture and shear and the building would collapse, when the expectation would have been that the building should have easily survived to preserve health and safety.
The consequences of this quake are tragic. An estimated 10,000 die. Another 50,000 are injured. But with the right formula, structures made of concrete can endure thousands of years. The ingredients for concrete have stayed the same for centuries. But there has always been room for innovation. With special ingredients and slight adjustments to the formula, concrete can adapt to the challenge of a specific project. Want a dam to hold back 52 million gallons of water? Add less aggregate to the formula to create a concrete with greater density. Want to create the foundation of an epic skyscraper? Add less water for a faster drying mixture. The array of different recipes is virtually infinite. The hunt for the right formula for a specific project is nothing new. The search for the strongest and most durable recipe goes back thousands of years. Although other civilizations, including the Egyptians, experiment with concrete, the Romans transform it from a supporting material to a main substance. In Rome, liquid rock fuels the dreams of an empire. The word concrete even originates in Rome. From the Latin concretus, it means grown together or compounded. Roman concrete contains the traditional ingredients of sand, water, and crushed rock. But volcanic ash from the hills of Pozzuoli, Italy, transforms the material.
The Romans were very astute architects and engineers, and they recognized that by mixing volcanic ash from Lake Pozzuoli in Italy, they were able to get a concrete that became very hard.
This volcanic ash proves to be an adhesive binding agent. It gives ancient Rome a powerfully strong concrete. This innovation allows the Romans to craft an empire from the ground up. Concrete becomes the backbone of a dizzying array of structures, aqueducts, bathhouses, and markets. But today, one structure alone stands as a unique testament to the power of ancient Roman concrete: the Pantheon.
The Pantheon is one of the great architectural works of ancient Rome, with the wonderful colonnade that introduces the building, and then a huge drum covered by this amazing 142-foot dome, and that dome is made of concrete.
Constructed around 125 AD, the Pantheon has stood prominently in the center of Rome for over 1,800 years. It is one of the world's oldest buildings in continuous use. This former temple to the Roman gods combines elements of engineering and design, and nowhere is that more apparent than in this concrete dome. Stretching 142 feet in diameter, it is the largest surviving dome from the ancient world. It was the largest dome in Western Europe until the 15th century. Unlike modern-day domes, which are generally reinforced, the only material holding the dome of the Pantheon together is Roman concrete.
Constructing an unreinforced concrete dome on the scale of the Patheon is just an incredible engineering achievement. You couldn't do something today because everybody would have praised the odds of your success as so small as you would never get a chance to do it. There's actually 7 different types of concrete used in the construction of the Patheon Dome. And the way they distributed their aggregate and changed the composition of their concrete so that the areas that had to take tremendous compressive loads, like the weight of the dome at the base, the aggregate is huge, 9, 10-inch rocks. But as the dome gets near the top, of course, there's less weight, so they switch over to pumice. Near the top ring is very high pumice content, almost 80, 90% pumice to make it lighter.
It is the Romans' ability to modify the formula for each stage of the dome's construction that allows it to stand to this day. The Romans also faced an immense engineering challenge: air bubbles. Pockets of air can form in the concrete during a pour. When the water dissipates, these holes can lead to cracking. To solve this problem, the Romans tamped the concrete, avoiding the need for excess water. By removing the air bubbles, the Romans increased the dome's strength and stability. The Romans also wanted to reduce the overall stress on the dome. To do this, they created sunken panels called coffers. These panels are decorative, but also take weight off the dome. They are a synergy of architecture and engineering. However, there is one feature that stands out in the Patheon's design. The dome's interior was designed to look like the Roman heavens. It features an interior circle called an oculus, or great eye, representing the sun. 27 feet across, the oculus is the source of all light for the Patheon. The oculus reduces the amount of weight and stress at the center of the dome, giving the whole structure added durability and strength. It is an engineering marvel. The dome of the Patheon is a stunning example of how Roman concrete could be built to last. Each layer of the dome becomes less dense the closer it gets to the top. At its weakest point, the Romans designed an oculus which reduced weight and stress. These innovations continue to impress engineers almost 2,000 years later.
For 1,500 years, that was the largest dome ever built by man. There aren't many engineered structures that stand that kind of record of time. And then all the countless use the Romans made for engineering aqueducts and other structures, roads, that made their civilization come together. So it's very difficult to imagine the Romans without concrete technology.
The Patheon's one-two punch of engineering know-how and architectural innovation influenced many structures to come. Thomas Jefferson's Rotunda at the University of Virginia, the Low Library at Columbia University, but none comes close to the Patheon's lasting power. With the fall of the Roman Empire, concrete is relegated to a supporting role. It is no longer the building material of choice. All that remains is the engineering brilliance of the Patheon and other Roman structures made of concrete. Now go back inside the science of concrete. It has been called an American pyramid. The mighty Hoover Dam is a testament to the power of concrete. Weighing 6,600,000 tons, this concrete colossus holds back 45,000 pounds of water per square foot. The force of this water generates hydroelectric power for over 1 million people. From the neon lights of Las Vegas to the freeways of Los Angeles, this hydroelectric dam generates 2,080 megawatts of electricity. The Hoover Dam's construction redefined what the world could do with concrete, but it also rerouted one of America's greatest rivers, flooding ancient canyons, reshaping the area's natural habitat. In 1905, the Colorado River breaks free of a man-made canal. It floods Lower California across 150 square miles. Epic floods wipe out thousands of farmers. Millions of dollars are lost. The Colorado is unpredictable. The Southwest also has another problem: power. The boom towns of Los Angeles and Phoenix are growing at a rapid rate and desperately need energy. Raging floods and lack of power, two different problems. But engineers believe there is one answer to both: dam the Colorado River. A hydroelectric plant would harness the natural power of the Colorado and, using simple mechanics, convert that energy into much-needed electricity.
You're generally looking in the construction of a dam for a huge, solid structure. It's really about holding back enormous quantities of water.
The dam needs a material that is strong enough to hold back the raging Colorado. And since the location would be remote, able to be made on site, one material can meet all of those requirements.
It's hard to imagine the Hoover Dam being built out of any material other than concrete.
Using steel on this scale would be too costly. But to make the Hoover Dam, engineers would need more concrete than had ever been used before in one project. The dam will be 726 feet high and 1,244 feet wide. With a structure this big, it will be impossible to do one massive pour of concrete.
The amount of material that went into this dam was so enormous that there's no way to pour the concrete in one segment. So what they did is they divided the whole dam into lifts and then into individual blocks.
The Hoover Dam needs to be built as a series of individual blocks that will interconnect. Trapezoidal in shape, the blocks rise in 5-foot lifts. This crucial engineering element allows the project to progress in stages.
Something on that scale being built in concrete had not been built before. Hundreds of pounds per square inch, thousands of pounds per square foot on the base of the dam, trying to push the dam downriver. And now you've got the Hoover Dam to stand this incredible water pressure trying to push it down the river.
Chief Engineer Frank Crow knows the completed dam will have to hold back 45,000 pounds per square foot of water. For this, they need a special high-strength formula. Crow's solution? A minor but crucial modification to the standard concrete formula. A very dry mix, one that uses less water.
More water makes it more workable, but shrinks more, and shrinkage causes cracks. The less water, down to 7%, the better and stronger the concrete.
The dam's remote location also means crews will have to build 2 concrete mixing plants on site. Shipping a very dry concrete formula from a facility far away would render it useless by the time it's transported to the dam. Because speed is of the essence when working with a very dry concrete mix, the crews working the pouring cranes have to push themselves to the limit to pour quickly and accurately. Now go back inside the science of concrete.
The process by which concrete cures, we call an exothermic reaction. By that I mean it gives off heat. And indeed, if someone pours a sidewalk or driveway around you, right after the slab dries enough to touch, put your hand on it. It'll feel warm. That exothermic, it gives off heat you can feel, sensible heat. As the amount of concrete going through this chemical reaction gets bigger and bigger and bigger and bigger, the amount of heat that's given off gets bigger and bigger and bigger.
Engineers calculate that if the dam were built in one continuous pour, the concrete would get so hot that it would take 125 years for it to cool to normal temperatures. The extreme heat would also cause the concrete to crack and crumble away. Concrete dries from the outside in. If the concrete is not evenly cooled, it can crack, putting the stability of the whole structure at risk. Instead, Frank Crow and his team of engineers have an innovative solution. Each block is outfitted with coils of thin-walled steel pipe. When the concrete is first poured, water from the Colorado River circulates through these pipes. The idea is to initiate a cooling process, but one done in stages. Cooling the concrete too quickly will cause it to crack. After the concrete has received its initial cooling, chilled water from a refrigeration plant is circulated through the coils to finish the cooling process. As each block is cooled, the pipes are cut off, and they are filled with grout by pneumatic grout guns, pumping 300 pounds per square inch of filler. Once the individual blocks have cooled and set, there is one final challenge. In order to prevent the hairline fissures between the blocks from weakening the dam, the individual blocks are formed with vertical interlocking grooves. When the concrete has cooled, grout is forced into these joints, bonding the entire structure into a monolithic concrete giant. This method takes advantage of one of concrete's fundamental properties.
Concrete as a material is very strong in compression. To build a structure, to make sure that the concrete is all in compression, you bend the beam like this, so now the water pushes on a column. Well, what's the water trying to do? It's trying to push that through. Well, it's the Patheon dome again. Only this time it's the water trying to do it. It's trying to push the dome through the river gorge. What that does is put the whole structure in compression. Well, concrete loves compression.
The more it is forced together while setting, the stronger concrete becomes. As a result of this property, the Hoover Dam is arguably stronger today than it was on opening day, 70 years ago. The Hoover Dam is a testament to engineering know-how and a skillful use of concrete. The dam contains enough concrete to pave a strip 16 feet wide and 8 inches thick from San Francisco to New York. More than 5 million barrels of cement were used in the Hoover Dam, and a total of 21,000 men worked on its construction.
And it represented an enormous engineering achievement to build successfully. It took the lives over 100 men to build that dam.
Today, the concrete mega dam is nothing new. But Hoover set the stage and showed the world that concrete could do the job and help generate much needed power. It changed the course of one of America's wildest rivers. Now the question is, can concrete conquer the skies? Now go back inside the science of concrete. In the scorching Persian Gulf, a growing structure cuts the horizon. Its expected height is a closely guarded secret, but experts around the world agree the Burj Dubai may be the world's tallest skyscraper.
It'll be the tallest building, for sure, the overall title holder for some time to come.
A construction project this massive needs 11 cranes and the world's fastest high-capacity construction elevators. The building rises at the breakneck pace of 1 floor every 4 days. And from the walls to the floors, to the columns to the stairs, much of this desert skyscraper is concrete. More than 160,000 cubic meters of it. At more than 2,000 feet, the Burj Dubai will be the crown jewel of the United Arab Emirates and is a shining example of a new generation of skyscrapers that seek to dominate the skies. It is a far cry from the humble beginnings of the concrete skyscraper, more than a century ago. At the beginning of the 20th century, the building material of choice was not concrete, but steel.
You can build a hell of a skyscraper with steel. In fact, the Empire State Building is so overbuilt, you could probably add another 30 stories to it under today's building codes, and it would still comply fine. So steel was a great material. You can build a great building from steel, but it's an expensive way to go.
And steel is not only costly, but represents a challenge for a new generation of skyscrapers that grow increasingly higher.
And if you're going to go tall, the building's got to be stiff. It is so much easier to make those thick, stiff walls from reinforced concrete than steel that it's a no-brainer. The Petronas towers in Malaysia are concrete, and this new one in Dubai is going to be concrete. If you're going to go that high, it's going to be concrete.
The stiffness of concrete, combined with its availability and relatively low cost, have made it the building material of choice for these new skyscrapers.
As our experience and comfort level with reinforced concrete came along, and as the buildings started getting taller, reinforced concrete really became the material of choice.
Before 1902, the tallest steel reinforced concrete building is a paltry 6 stories tall. The Ingalls building in Cincinnati changes that. Engineer Henry Hoover dreams of a monolithic building of concrete, a skyscraper 16 stories tall. But many engineers believe that a concrete tower 16 stories high will collapse under strong winds or even its own weight. When Hoover finishes his building, there are many skeptics.
There's one anecdote that says that a reporter actually stayed up all night waiting for the Ingalls building to collapse because he was so certain that it was going to. Needless to say, the reporter was disappointed in the end.
It is a towering success for its time. But at 180 feet, it is just one in a dizzying array of modern-day skyscrapers. More than a century later, the towering dream of Dubai aims to be over 10 times the size of the Ingalls building. Every morning, workers assemble in the garage of the building. Erecting this much concrete in the punishing heat of the Gulf requires serious manpower. But before workers can pour a drop, the perfect formula needs to be mixed at the batch plant. The first problem this leviathan from the desert faces is its own height. The taller a building, the more it flexes, increasing the likelihood that it could flex to the breaking point, a deadly proposition. Older skyscrapers like the Empire State are safe because they use massive steel beams and braces. But erecting a tower nearly twice as high requires a material with even greater shock-absorbing qualities.
If you take something like the Empire State Building and the wind blows on the Empire State Building, well, the wind creates pressure, which are going to try and bend the Empire State Building over. But as you go higher, imagine now going twice the height of the Empire State Building. The wind gets more surface to work on. Indeed, buildings collapse when the flex is so great that the weight of the building gets outside of its footprint and the building doesn't have strength enough to handle that. Down it comes.
Now go back inside the science of concrete. Builders will need a formula that is almost as strong as cast iron, yet more resistant to damage due to vibrations from the wind. After extensive computer and wind tunnel testing, the architects behind the Burj Dubai will use a high-strength concrete formula. It contains slag, a byproduct of the steel industry, and microsilica, which gives the concrete added strength.
If you look at the microstructure of concrete, there are many, many spaces between the particles that are either hollow, so we call them pores, or they are filled with water. Microsilica plays the role of filling these pore spaces between, and therefore it makes concrete much more dense, more durable, and stronger.
And in order to make sure that the formula is consistent, Alam Feroz, quality control manager for the concrete of the Burj Dubai, routinely tests the concrete before it is used in the skyscraper.
I'll give you an example. Like if you're giving a blood to a patient, so how important is the blood to be tested before you give to the patient? It's a big risk. So same is with the concrete. When it has been tested, I get confident that whatever I'm giving to the structure is being tested and it complies to the requirements. It won't be just a mere guess.
To test the strength of the concrete, small cubes are hardened in cool water. Next, the concrete is deposited into a crusher for a stress test. This cube holds up to nearly 14,000 pounds per square inch, making it a high-strength concrete. The concrete test has been successful. But as strong as this formula is, it still has to contend with desert heat. Temperatures top 120 degrees. How do you keep concrete cool in the desert? Builders use a deceptively simple technique. Shaved ice. While it's being mixed at the batch plant, slices of ice are mixed into the concrete so that it remains cool inside of the mix trucks. When it arrives at the building site, the melted ice has kept the concrete from overheating. But now, the concrete has to travel hundreds of feet into the air.
The key technical problem for building a building of this size and of this height is going to be to vertically pump concrete of the order of 2,000 feet high. It takes huge amounts of pressure.
Mixer trucks deliver the mix to the pumps. The building requires 3 pumping stations where the liquid concrete is poured. The high-pressure pumps force the concrete through a complex system of pipes.
Now, the technology to do so is awesome. If you think in terms of water, you have 1,000 feet of hydraulic water pressure. That's a tremendous kind of pressure. Now, concrete weighs 2.5 times as much as water. So you need a piping system that's so much stronger, and also pumps that are so much more efficient to pump concrete up that high.
As the sun sets, the second shift workers return to feed this growing skyscraper. The concrete pour takes place at night so that the concrete can harden evenly.
At the moment, even though it's 10 o'clock at night, it's about 100 degrees Fahrenheit, and the humidity is about 90%. The advantage of pouring concrete in these conditions, because the humidity is so high, we don't have a problem with it drying out the top surface of the concrete, but we've got effectively another roughly 130 stories to go.
As the pour continues into the night, the Burj Dubai has reached a milestone. 25% of the building is done. When completed, this megastructure will stand over 2,000 feet tall, making it twice as high as the Empire State. It will be covered in a reflective glaze to protect it from the extreme heat and high winds of the Gulf. But the building's guts are solidly concrete. When it's finished in 2008, the Burj Dubai will be the tallest building in the world. Like the Ingalls, the Burj Dubai has set the standard for its day, showing once again that concrete can be used in a variety of ways for the world's tallest buildings. Now, reinforced concrete is establishing itself as a building material of choice for skyscrapers. Concrete has conquered the skies. Concrete's next quest, how to tackle the building challenges of the future. Now, go back inside the science of concrete. Concrete has been a key ingredient in the construction of our civilization. It has been a fundamental part of our architectural past and is now paving the road for our future. Scientists are developing new formulas for concrete and are looking for ways to make it stronger, more environmentally friendly, and capable of doing things we never thought possible. Back where it all started, at the heart of the Roman Empire, concrete has taken a new and exciting turn. Just a few miles from the Patheon, the Jubilee Church, designed by architect Richard Meyer, uses a new form of concrete. The church was commissioned by the Archdiocese of Rome to commemorate 2,000 years of Christianity. For that, the building would need a material that was both ancient and modern, a material that would speak to the church's past and make a bold statement for the future. They would also need a material that would last the test of time. Concrete fits the bill.
This church is remarkable for several reasons. It has these three sail-like forms, loosely representing the Holy Trinity, but made in effect of giant concrete blocks.
The shells of the church, which stretch out and up in the same way as the Sydney Opera House, are made of 346 white, reinforced, precast concrete blocks.
Concrete, for all of its advantages, does tend to pick up discolorations from the atmosphere and so on. Meyer, though, wanting to keep his building white, managed to work with local firms in order to achieve this concrete mix that included these photocatalytic particles that will absorb and neutralize the acids in the air. And in effect, what you'll have is a pollution-eating building.
Italcementi came up with a revolutionary new formula for the concrete that will keep it as pristine in 50 years as it was on opening day. All concrete structures tend to stain and degrade from pollution. Over time, this has given concrete a bad reputation. But the unique formula for the Jubilee Church contains a secret weapon: photocatalytic particles.
Now, in effect, what these do, when activated by the light of the sun, they mix with the acids in the air and neutralize those acids, neutralize the discoloration that would come typically from atmospheric pollutants. So, in a way, you kind of have a self-cleaning building.
This test demonstrates the photocatalytic particles at work. The concrete neutralizes pollutants, allowing it to maintain its brightness and not degrade over time. It is a revolutionary new development that has the potential to transform the way we look at concrete forever. Concrete isn't just working harder, it's working smarter. New developments in concrete technology now allow for what used to be unthinkable: helping the environment by using an unusual aggregate: glass.
The innovation here has been in making sure that the glass doesn't get corroded by the lime in the cement mixture. One of the biggest issues with concrete is that the Portland cement tends to be quite corrosive, and this has been a big problem with things like recycled glass. It tends to corrode the glass falls out. This composition of cement was actually developed by Columbia University. It is a much less corrosive, more benign cement, allowing you to put the glass chips in. So you can actually now have concrete with glass chips that actually has a good surface effect.
We are generating millions of tons of garbage, solid waste, and in New York City, approximately 6% of all solid waste is glass. That's bottles like this, yeah? And these bottles generally find their way into landfills. And that costs taxpayers hundreds of millions of dollars just to get rid of these bottles.
Concrete's versatility allows it to bind with other materials, in this case, glass. The first step is to separate the bottles by color.
And then you crush them in a crusher. Now, crushed glass is not something like this. This is what we call broken glass, and that is something you want to handle very carefully. It has sharp edges, and that was also one of the problems we were facing, because skeptics asked, well, if you use glass in concrete, won't people cut their hands by handling the blocks or whatever? Answer is no, because when you crush the bottles in a high-impact crusher, it comes out in pieces like that, and it's just like sand. It does not have sharp edges.
Eventually, the broken glass is crushed into a fine powder.
So this is just like powder, like baby powder, the same kind of particle sizes. So if you put this finely ground glass powder into concrete, you can replace part of the cement by this glass.
These are actually 100% recycled glass pieces added into the concrete.
Initially, scientists thought that recycled glass would make for a bad aggregate. But Professor Meyer and his team have found a way.
Okay, so once you make concrete out of these glass particles and color coordinate it very well, then you can get something like this, and this is now already being commercially produced. That's the way how regular concrete would look. And this is here our glass concrete, polished to a high precision, high grade of polishing. And that is known as terrazzo concrete.
Using recycled glass as an aggregate is just one of the many ways that concrete continues to reinvent itself. It also may pave the future for a more environmentally friendly concrete. There are also other developments reshaping concrete for the future. For the last 100 years, architects and builders have sought a way to allow light into concrete buildings, homes, and offices in a more efficient manner. One of concrete's biggest drawbacks is that it creates dark buildings that do not effectively conduct light. Experts are working to change this.
Okay, this is a piece of litricon, light transmitting concrete. It seems like an odd concept, but what they've done here is to take standard concrete and add glass fibers. Okay, so what you're seeing here is the blue LED passing through the glass fibers that are embedded in the concrete.
Imagine concrete allowing light to pass right through it, or for someone to cast a shadow through a concrete block.
The same thing can happen with normal daylight as well. So the idea is that you can build a structure with this concrete and allow daylight to actually come through the structural element of the concrete.
Light transmitting concrete, or litricon, is a unique form of concrete that uses glass fibers to conduct light. It allows for massive structures to permit light to shine through. This technology has the potential to redefine what concrete looks like. Once considered cold and impersonal, these new forms of concrete are transforming the material. What started off as the most basic of building materials is now on the cutting edge of building and design. The future for concrete is virtually limitless. If concrete is anything, it is a material that continuously reinvents itself. Concrete continues to adapt to the emerging challenges of our world and is laying the foundation for our future.